Alright, hello and welcome back to our fun proofs lectures, and I think we're going to finish up the slides today. So we stopped on this problem right here, and I wanted you to try and prove this using contrapositive. So for any integers x, y, and z, if x divides y and x does not divide z, then x does not divide y plus z. Not too bad, but I kind of tricked you. So there's a normal way to make the contrapositive of this, and it's not very easy to prove the statement. There is another way. So let us visit the next slide before we prove this. Okay, so let's talk about contrapositives when you have multiple hypotheses. Okay, maybe I should put the question marks over here. So sure, you got your P implies Q, that's equivalent to not Q implies not P. That's fine. But what if you have multiple hypotheses? And here you totally do. It's like if this and this. Yeah? So what do you do here? Well, you can do the same thing. You can negate this, flip it, and negate that, which ends up giving you not R implies not P and Q, which, using De Morgan's laws, gives you not R implies not P or not Q. So it's like, okay, if R is false, then either P is false or Q is false, or maybe both. But you do have more options than this, okay? You have more than just saying this, because you can bring this one back in if you would like, because this is equivalent to saying, like, again, right here, not P or something. This is equivalent to P implies not Q, right? And you have your not R at the front here. So it's like that implies all that. So if not R and if not P, then not Q. And so you can bring these together with an and. Boop. And not R and P implies not Q. So these are the same. Okay, so it's this is equivalent to saying this, which is weird to think about. It's not always obvious, and in one of your homework assignments, you'll also need to use this kind of idea. So this is saying something like, okay, if R is false and P is true, then Q must have been the one that was false, because this is saying, okay, if R is false, then one of them is false. This is like, okay, if R is false and P is the one that's true, then Q must have been the one that is false. Okay, so it kind of makes sense in English too, but that's not a good place to think about things that are logical. Okay, so we like to use symbols for that, just to confirm that all this is the case. Okay, so we can use this, in fact, and it makes it a lot easier to prove this. So like the normal contrapositive way would be like, okay, I see if this and that, so here's my like P, here's my Q, here's my arrow, and here's my R. Normally this would be like, okay, I'm going to negate R, so x divides this time y plus z. That implies, okay, it's not true that x divides y, so x does not divide y. Or it's not true that x does not divide z, so x divides z. And it's really hard to prove a not divide thing, okay? So that's the reason. We can bring this back over here, is the idea, using our equivalences. So we can do that. We can say, okay, this is equivalent to saying if x divides y plus z, and x divides y, then x divides z. So if you do this one instead, it's going to be a lot easier to prove. Okay, that's all. Okay, so let's give the proof now. So if you read the book and you're like, okay, gosh, I couldn't get this, or maybe I'm going to read the book now because I couldn't get this, then I clap. I clap for you, because this is a hard thing to notice that you need. All right, so again, here are our arbitrary integers. Assume that we have them. Assume this, and prove that. Are we ready? So we're going to assume that we have integers x, y, and z now. X, y, and z are ints. And we're also going to assume all of this, okay? And, I guess I don't want the and yet. Assume that x divides y plus z. And now I could say and x divides y. Okay, so what we would like to show is x divides z. Okay, so it's like a little comment to ourselves there. And okay, so we know, based on these facts, some information. So that means y plus z, it's equal to k times x for some integer k. Okay, so we have that. And we also have x divides y. So we also have y equals some other integer like mx for some m. So for some k and m. Okay, so I have these two facts. And now we need to show that x divides y. And so really what we're looking for, like if we could give a comment in our own proofs, it's like we want, in order to prove this, we need to show that y equals like some r times x for some r. We need to find that r somehow. Okay, so that is what we'd like to do. And once we've found it, we have proven the whole thing. Yeah? All right, so let's continue. So I know this, let's plug this into that. All right, so instead of y, I'm going to say mx. So so y plus z equals mx plus z equals kx. And oh man, are we in a good spot now, because I can subtract mx from both sides to get z equals kx minus mx. And I can take an x out, of course, equals x times k minus, or let's put it on the other side because for reasons. So here's the x over here, k minus m. That is an int because k and m are ints. And so I have that z equals k minus m times x. So that's my r, all right? Let's see here. Dun, dun, dun. Oh, sorry, I wanted z equals r times x. My bad, you're probably yelling at me through the screen right now. I wanted z equals r times x, and I've just found it. Okay, there it is. I'm proving that x divides z, so z equals some r times x. Excuse me. And we just found that r is the idea. So z equals k minus m times x, and k minus m is an int so we then have that x divides z, which was what we needed to show. Okay, and that is the entire proof. Isn't that fun? QED is what we were trying to show. We have proven the contrapositive of this statement by saying that if this is true and that is false, then this is false, is the idea. Okay, so that's the contrapositive, and we've looked at this slide, and it is very useful, and we will move on now. Okay, so have one more before we go to a different style of proof. So give this a shot. Prove the following statement by contrapositive, and yeah, then we'll come back and try it together. So for every non-zero real number x, if x is irrational, then 1 over x is also irrational. So assume this, assume the negation of this, prove the negation of that. Yeah? So here's the if, here's my p, here's my q. So it's really saying something like, let's see here, let's negate this. 1 over x is rational. Implies that x is rational. And that's easy to talk about because we have a definition for what rational means. Okay, so let me have my proof now. So again, assume we have a non-zero real number x, and then we'll assume the negation of the conclusion and prove the negation of the hypothesis. That's the contrapositive. So assume x is non-zero, and 1 over x is rational. Okay, there we go. So now we have to show that x is rational. Okay, so to show TS, x is rational. It's like comment to ourselves again. So what does it mean for something to be rational? Let's go on up here to our handy dandy definitions. So a number is rational if there are two numbers. The bottom one can't be 0, such that your number equals the first number over the second number. Okay, so there's a ratio between things. So your number r equals some number over a different number. Yeah? So we have that. We get to assume that. So 1 over x is rational. So that means that 1 over x equals p over q. I've already used p, so let's use some different letters. Equals, I don't know, m over n. Let's try that for some m and n, which are integers, and n is not equal to 0. We may need that. Okay, so we just need to now show that x itself is rational. So we need to find some things such that something over something else gives us x, and then we will have shown that x itself is rational. All right? But if I take reciprocals, suddenly I have x. But x equals 1 over x. Okay, that's the idea. Dun dun dun. Which is supposedly equal to 1 over m over n, which is equal to n over m. And we can do this because x is non-zero. We can divide on both sides, okay? It's totally allowed, and now we are happy, okay? So we have found our numbers. We just now need to show that m itself is non-zero. And that's actually not too bad because we assume that x was non-zero to begin with. So if x was non-zero, that means that 1 over x was non-zero, okay? And therefore, m over n was non-zero, which means that m on top, the only way to make a zero rational number is for m to be 0. M's not 0. So you can write all that out. So let's see here. 1 over x is non-zero because x is non-zero, and same for m over n. Okay, so just by math you get that. And then suddenly we've found our two numbers equaling to x. Okay? So, let's see here. X is rational. Because we found these two numbers with the denominator not being 0, such that n over m is equal to x. X is the first number over the second number. Okay, so x is rational, which was what we were setting out to prove. And so bam, the statement's true. And so even though we proved something different, we really just proved this. Okay? We proved something about irrational numbers, which is really weird to think about. But it works. It has to be true because it's the contrapositive. It is equivalent. So for every non-zero real number x, if x is irrational, then 1 over x is also irrational. So we get that for free. It's just a part of our proof now. It's just a side condition of this being equivalent to its contrapositive. Isn't that fun? Okay, so that is proof by contrapositive. Just swap things, negate them, assume one thing, prove the other, just like you would do for a direct proof, because it is just another kind of direct proof. Now I want to give you a fun kind of proof. This one proves a lot of nice things, okay? It's a really good hammer to have, okay? It's called proof by contradiction. And you may have heard of it before. Maybe if you took like an advanced math class like real analysis, you will have used proof by contradiction a ton. But if you have not, don't worry, because I am excited to teach you about this. It's a fun one. So what you do with a proof by contradiction is you assume your entire theorem, the whole thing, you assume that it is false, okay? And then you find what's called a contradiction, which essentially means that you prove false, okay? So in essence, if your theorem statement, just pack it all into this thing called Q, what you do is you prove not Q implies false, yeah? And the reason that works, the reason it's equivalent, is because not Q implies false. Well, that's just not Q, or false. Oring by false does nothing, so that's just not Q. That's just Q. Equivalently, you could go by contrapositive. You could go, okay, negate this and then that, and flip them. True implies Q, which is... let's see, true implies Q is not true or Q. That's false or Q, which is just Q again. Okay, so there's a bunch of different ways you can get about this. At the end of the day, you're still proving Q if you prove this, which is weird. And the way you prove it is to assume this. It's just another direct proof at this point. Assume this, prove false. You have to prove that false is true, which is weird to think about. But here's the secret. You can only ever get false. It's really hard to prove false things ever. You can only ever prove true things. So what your job in a proof by contradiction is to find two statements. The thing that you assumed, and then some other thing that when combined gives a contradiction, because you can't have both of these at the same time. P and not P. That is equivalent to false. Yes? So you just prove those two contradictory things. They can't be both true at the same time, and then suddenly your proof is done. It's kind of anticlimactic in a sense, in that it doesn't make sense why you're done, but you are. You just proved the thing. So this is called an indirect proof because it feels a little weird. All right, so that is proof by contradiction, and I'm going to give you some fun examples now. So the first one is birthdays. So assume that you've got a group of 25 people, maybe like the students in this class, and the theorem is saying that there must be at least 3 students or people who are born all in the same month. And we're going to prove this by contradiction. So this is the entire theorem. We're going to prove the entire theorem by contradiction. So we say proof, and usually you want to warn people like by contradiction. And then you get started. You say, okay, assume this entire statement was a lie, and then we're going to derive false. We're going to prove a contradiction occurs. Okay, so among a group of 25 people, there must be at least 3 who are all born in the same month. So, okay, let G be a group of 25 people. So now this gets a bit interesting because we need to somehow negate this, or at least this fact. So there must be at least 3 who are all born in the same month. So there exists a month. This is kind of what it's saying. There exists a month such that greater than or equal to 3 people are born in that month. Let's say a month M. Greater than or equal to 3 people are born in M. And we need to negate this, which is giving us something like, okay, for all months, there are less than 3 people born in it, in the group. Okay, so this is the kind of thing we get to assume now. Just the whole statement was false. So assume, for a contradiction, that less than 3 people were born in each month. People in G, that is. People in the group that we're talking about. And we're going to use this to derive a contradiction. So, okay, from here, what do we know? Think about this for a second. It's an interesting fact. So if less than 3 people in G were born in each month, we're assuming that, because we're assuming this entire theorem was false, well, that means Well, less than 3 is less than or equal to 2. So there are at most 2 people in every month. Then the max number of people in G is 2 times 12, because you got 12 months, and we're saying that there's less than 3 people born in each month. And we could try all the months. We can't have 3 anywhere, but we can have 2 everywhere. So the maximum number of people that could be in G is 24. Ooh. Now this is a contradiction, because bam, bam, G has 25 people. We're saying that it can't have any more than 24. That's a contradiction. So that's pretty easy to see. It's called sometimes this legit happens in a proof. Somebody says contradiction exclamation point. There's also like a lightning bolt that stands for contradiction QED, and then you can also have your QED if you want. That's hilarious how math works, but we got to keep it fun somehow. So we assume that this entire theorem was false. You got a group of 25 people, and it's not true that there's at least 3 who are all born in the same month. So that means that there must, well, at most, everybody is born in a different month. You can't have 3 in any month, but you can have 2, okay? That's the idea. So at most 2 people born in every month. And that gives us a very strong statement about how big G must be. And it was not. It was actually bigger than that, so something's wrong. So if that was exciting for you, get ready, because I'm about to show you one of the coolest proofs around. It's a very classic example of proof by contradiction. It's showing that the square root of 2 is irrational. Okay, so it's not a rational number. It can't be represented by like a over b for some a and some b. So the way we do it is by contradiction. So proof by contradiction. And so what we're going to say is assume that square root of 2 is rational. That's the opposite of this entire theorem. Assume that square root of 2 is rational. Now using our definition of rational, we can say that therefore, sure, square root of 2 equals a over b for some a and b. And one key thing is I can have some side constraints on this a and b, because all fractions can always be reduced, right? Like 5 over 10 can be reduced to 1/2, but 1/2 cannot be reduced any further. So I can ask for this a and b that some genie is giving to me. For some a and b, I can say that, okay, they've been already reduced, okay? A to b such that a over b is fully reduced. It's a fraction that can't be reduced anymore. Okay, that's fine to assume. And then we're going to come up with a contradiction based on this idea. Okay, so what we can get is we can get 2 out of this by squaring both sides of this. So 2 equals a squared over b squared. And therefore, if we just bring the b over here, we have b squared times 2 equals a. And would you look at that? Oh, sorry, a squared. A squared equals 2 times some other number. Any number squared is still an integer. So a squared is even. And to go any further, to produce our contradiction, we need what's known as a lemma that appears on the next slide. So we need to be able to say that if x squared is even, then x was also even. Okay, so we're going to prove this by contrapositive. And a lemma, it's like a tiny little baby proof. Okay, it's just like a theorem. So you think of it as a little theorem. You're using it to prove some more important thing. So this is the important thing we're trying to prove, and we are proving this lemma to get there. So let's prove this quickly by contrapositive, so not this implies not that. So proof contrapositive. So assume x is odd, then x equals 2k plus 1 for some k, and then x squared, which, if we expand, we say x squared is equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1. And we can take a, I guess we can take a 2 out. We can take more than a 2 if we wanted to. Equals 2 times 2k squared plus 2k plus 1. And all this stuff is still an integer because it's math using integers, because k was an integer itself. So x squared is odd. Okay, and that was the contrapositive, so that's all we needed to show, just show that x squared is odd. So now we have a proof saying that if x squared is even, then x is even. Okay, so let's come back here and use that. So a squared is even by the lemma. A is even. Okay, because a is even, so these are all just falling together. It's a beautiful proof. So a equals 2 to the k for some k, and we can bring that into this this equality. So 2b squared equals 2k squared equals 4k squared. And oh man, I can divide by a 2. I got 2b squared equals 4k squared. I can divide by 2 on both sides. I can go to b squared equals 2k squared. And now I can play this whole game over again. B squared is now 2 times some integer, so b squared is even. And that means b is even. By the lemma, oh man, so b equals 2 to the m for some m. And therefore, dun dun dun, square root of 2 equals a over b equals 2k over 2m can be reduced. Do you see that? This can still be reduced. So it wasn't actually in a reduced form. It wasn't fully reduced to begin with, even though we assume that. So we have it wasn't fully reduced, and it was fully reduced. False, contradiction, QED. Yes? So that was a bit of a journey, but I hope you see how fun these kinds of proofs are, and you can just follow all the little trails, and eventually you'll get to the answer. And proof by contradiction is quite powerful because we don't have to deal with like irrationality anymore. We can prove things about rationality. You see that? So that's a lot easier because we can define rationality very easily. So that is a really cool proof. I hope you think it is cool too. And yeah, now it's your turn. So prove the following statement by contradiction. If a group of 9 kids, they won a total of 100 trophies, so they were competing for something, then at least one of the 9 kids won at least 12 trophies. Okay? So give that a try. And so by contradiction, we get to assume that this is not true. None of this is true. So there's a group of 9 kids, they won 100 trophies. At least one of the 9 kids won at least 12 trophies. So if this last fact is false, let's assume, for contradiction's sake, assume all 9 kids won less than 12 trophies. So that's at most 11. Okay, you see how this is similar to the other example above? Okay, that's all well and good. That means that the number of trophies, the total number of trophies, was at most, because they can win less than 12. Some kid might have won 1, some other kid might have won 11. But at most, it could have been everybody got 11 trophies. Okay, so it was at most 9 times 11 equals 99. But we were assuming that there are 100 trophies. But there are 100 trophies total. Okay, so that and that make a contradiction, and hopefully you see it. Okay, not too bad. I'm of course not going to ask you to prove that the square root of 2 is irrational on any kind of test or even on your homework. So that is, this is kind of more the style that I'm going to give you. All right, so that is proof by contradiction. You are now masters at it, and the rest of this is called proof by cases. Okay, so sometimes you're proving a for all proof, and it's really hard to just say, okay, assume x is arbitrary, let's prove p of x. Or assume a is arbitrary, let's prove p of a. Sometimes it's hard to use just one arbitrary element, and you don't have to. As long as you cover the entire domain, you don't have to stick to just one. So you can split the domain up into different little classes. So if like this is your domain, it's got this stuff over here and this stuff over here, and they're all kind of different. There's like 3 things that are all kind of different. You can do it like this. You can prove one proof for this one, and then for that one. That's the idea. If you give a different proof for each class, they still all come together to be covering the entire domain. Okay, so for example, if you're trying to prove something about integers, it might be easier to give a different proof for an arbitrary x when x is less than 0, an arbitrary x that is equal to 0, and an arbitrary x that is greater than 0. If you do these 3 proofs together, you've suddenly covered all of the integers. Okay? Together. Cover all ints. Okay, that's the idea. So for example, let's define that the absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. That's a standard way of defining the absolute value of x. So let's prove now that for all x, the absolute value of x is greater than or equal to 0. And you can see where the cases kind of naturally arise, because it's like, okay, if x is greater than or equal to 0, I have one thing. If x is less than 0, I have another thing. So now I can break it up into those 2 cases, and I have an easier proof. Okay? So, proof. Tiny proof down here. So, let's see. Case 1, x is greater than or equal to 0, so x is arbitrary, we can assume. Case 2, x is less than 0. So, in case 1, the absolute value of x is defined to be x. And, well, the absolute value was, of course, greater than 0 because x itself is greater than 0. Okay? Greater than or equal to. So that one's check. X is less than 0. That means that absolute value of x is negative x equals negative x. And if I negate this, if I go x less than 0 and I negate the entire thing, I get negative x greater than 0, yes? So I get that's greater than 0, which is totally greater than or equal to 0. Yeah? And so that's my case 2. I've proven that in that case, absolute value of x is greater than or equal to 0. So that's the entire thing. I've proven it for an arbitrary x in both cases. Bam! I've proven it for every x. And it was easier that way because of the thing that I was trying to prove. That is, that's the essence of the idea there. So that brings us to W log, log, or if you say it in full, without loss of generality. Okay? So the idea is sometimes you're proving something and your theorem can be split into multiple cases. You got one case with this picture, that's how you prove it, and another case sometimes looks exactly the same, but it's just slightly different, okay? So the idea is, usually, you don't want to give the second side because it's so obviously the same as the first, just slightly different. And so we just say, without loss of generality, I'm going to prove this side, and you can figure out that the other side is easy to do if you ever needed to do it. Okay, it's exactly the same. So if you have two or more cases that are symmetric like this, it's sometimes obvious that they're both true if just one is true. So you can say, without loss of generality, I'm going to give a proof for just this one side. Okay, for just this one case. Okay, so let me give you an example of this quickly, and then we will move on to our last slide in the set of slides. So, as an example, let's say there are two integers, x and y. If x is even or y is even, then xy is even, we say. Okay, so the idea is, well, either x is even, or y is even, or both are even. And you kind of have three cases, but you really only need two, because I can use only the fact that x is even. I can take that y is anything to prove that xy itself is even. So let me show you one side. So assume, for this proof, assume that x is the one that's even. Then I need to show, remember that we need to show xy is even. Then x equals 2 to the k, or 2 times k, sorry. And that means xy equals 2ky, which equals 2 times ky, which is an int, and therefore xy is even, and that proves that case. So I think you can see that if I just replaced x with y, x with y, x with y, and y with x, I get the same proof, okay? So let me just write that over here for posterity's sake. Swapping, let's say. Swapping x and y in the proof on the left proves the case for y. Proves the case where y is even. So we don't need to give it. It's too similar, okay? So what you do is say, assume without loss of generality, because that's the case here. Assume without loss of generality that x is the one that's even. I'm going to show you a proof, and it's pretty obvious that if y was the one that was even, on the other hand, that you could push this proof through the same way, because essentially xy is yx. There's no difference. That is the idea of log. Okay, so now you know it. And now we're here to the last slide. So this is going to be a proof by cases. Okay, so I want you to prove it. This following statement, if x and y, they're integers, they have the same parity, and what that means is they're either both odd or they're both even, then x plus y is even. Okay, so give that a shot, and then we'll come back and do it together. So here we go. Proof. And we have, I think you see that there are two cases. Either they're both odd or they're both even. So case 1 over here. So they're both odd. If only I could write better. Both odd. And then case 2 will prove over here. Case 2, where they're both even. All right. So in case 1, they're both odd. So let's say, assume that x and y are both odd. That means that x equals 2k plus 1, and y equals 2 times m plus 1. And then we have to say that x plus y is even. Okay, x plus y equals, bringing all these in to the statement, 2k plus 1 plus 2m plus 1, which equals 2k plus 2m plus 2, which you can take a 2 out of, k plus m plus 1. So it's even. So x plus y is even in this case. All right, case 2, assume that they're both even. That means x equals 2k, or 2 times k, and y equals 2 times m for some other integer. Doesn't have to be the same one. It could be the same one, but you never. It's like existential. You're instantiating an existential variable. It needs to be a different one each time you undo an evenness definition. All right, so x equals 2 times k and y equals 2 times m, and so it's pretty easy to see that x plus y equals 2k plus 2m equals 2 times k plus m. Okay, and so that's an integer, and so x plus y is even in that case. Okay, so in each case, it follows through, and this covers same parity, and so we've proven every possibility, and so we've proven it for all x and y that have the same parity. Yeah? And that's it. We did it. Good job. So that is the end of these slides for the week, and I think that's where I just want to stop, probably. If I don't edit this video to give you a quick introduction to the next set of slides, then you can assume that I will see you later. So, yeah, I will see you soon.